hello and welcome to the 31st lecture in this series, and I was giving some examples of vector fields last time. So in particular I had this, I gave an example of a vector field on S1 at the point xy. I am looking at xy. Now notice that in fact this example can be generalized to all odd dimensional sphere. In fact, on S2n plus 1 contained in R2n plus 2 for any n bigger than or equal to 0, I can write down a similar vector field. So let's start with a point x1, p equals x1, x2, x2n plus 1, x2n plus 2. So let's start with this point in the sphere, 2n plus 1 dimensional sphere. Again, the tangent space to the sphere in any dimension we know is given by the regular value theorem. The tangent space is still given by the right hand side. It looks at the point P, it consists of all vectors V such that V in a product with P is 0 as a subspace of the ambient Euclidean space. So in this case too, that's the case. So I just, to come up with a vector field, I just use x at P. Well, I just take minus x2, x1, and I just put zeros elsewhere. This will give me a smooth vector field on the 2n plus 1 dimensional sphere. And in fact, I can play around with this and come up with other ones as well. Yes, that's, or another example would be xp. I do this on each pair of variables. Minus x2, x1, minus x3, rather x4, x3, and so on, minus x2n plus 2, x2n plus 1. All I have to do is ensure that xp is perpendicular to p, which is this. P is here. So the way I've written it, it is perpendicular to this. So each of this gives rise to a smooth vector field on two-dimensional sphere. So this is in Tp S2n plus 1, and so is this. And the smoothness, again, these are all, even though I have defined it only for P in S2n plus 1, if I use the same formula, this is a vector field defined on the whole of Rn, whole of R2n plus 2. So, but so we again use this small proposition here that if I have a vector field on the whole manifold which is tangent to the submanifold at each point, then the restricted vector thing is also smooth. So these are all smooth vector fields. The last one, this is especially interesting because it gives rise to a vector field on the sphere which is not 0 at any point. it cannot happen that this vector, you get the 0 vector, because if this is 0, then the coordinate vector would also be 0. P would also be 0, which is not the case since P belongs to S2n plus 1. So the existence of a vector field which is not 0 at any point is related to some questions in topology. But we are not going to go into that. Instead, let's talk about, this is the right place to talk about Lie groups. So this was example number 3. Now I am moving on to example number 4. Lie groups and Lie algebras. So let G be a manifold with a group structure. I'll quickly recall what a group structure is, but let's assume for the moment, let's proceed with a group structure which is compatible with the smooth structure in the following sense. I just demand that group multiplication, which is a map from G cross G to G, xy going to x times y. The map and G going to G, x going to x inverse. I demand that these two maps, so the maps, these two maps are smooth. So, so in order for this to make sense, we need a notion of a group. So, groups is a set with a binary operation, also called group multiplication, and what a binary operation just means that if you start with the same thing that I've written here, G cross G to G. So a binary operation is just a map from G cross G to G, but satisfying such that one G operation is associative. So in other words, G1, G2, G3 is G1, G2, G3. Secondly, there is an identity E in G. And the definition of an identity is that EG equals GE equals G for all G. And every element G in G has an inverse And this definition of inverse is that G inverse equal to G inverse G equal to identity. So that's a group. So now the thing is that but here normally when one first sees this notion of a group, this G will be typically a finite set, say the group of permutations, etc. Now here it's definitely not going to be a finite set if the dimension of M dimension is greater than 1, dimension is at least 1. So let G here we have a manifold and which has a group structure as well, which is compatible with the smooth structure. It's not that the group structure and the manifold structure should be completely independent. They should be related in the following sense, that the group multiplication and inversion operations are smooth maps. Here G cross G is regarded as a product manifold. But the good thing is that one has lots of natural examples of this. So such a G is called a Lie group. So one can think of it as a manifold which is a group, or a group which is also a manifold. So examples. Any vector space is trivially a Lie group. Now the group operation here, the binary operation here is just addition of vectors. Even though here I said the binary operation is called group multiplication, when we are in the context of vector space, multiplication means actually addition here, addition of vectors. So any vector space with vector addition is a group, and we know that vector spaces are also manifolds, and we know that the addition operation is smooth. To say the addition operation and the inversion operation is just x going to minus x in this case, and those are smooth simply because ultimately the manifold structure comes from identifying an n-dimensional vector space with Rn, and when we do that, this addition in the vector space just corresponds to usual addition of vectors in Rn, so which is certainly smooth. Now more interesting examples come from looking at matrix groups, which I'll talk about shortly. But before that, it turns out that there are even spheres. Some of them are groups. So S1, for example, is a Lie group, and in fact it turns out that S1 and S3 are Lie groups. Let me just take the case of S1. Now the group operation on S1 is comes from regarding S1 as the set of complex numbers with modulus 1, and if you think of it S1 in that way, then of course we can multiply two complex numbers, and if both have modulus 1, then so does the product. The group structure on S1 arises by regarding S1 as set of all Z in C with mod Z equal to 1. So if you think of it like that, then Z1, Z2, we just do usual complex multiplication. Of course, this is how one gets the structure, but ultimately one doesn't have to mention complex numbers at all. So one just uses this complex numbers as a motivation and then define. So if I just start with x1, y1, x2, y2 in S1, then I define the product x1, y1 times x2, y2 to be, well, I just do complex multiplication of x1 plus iy1, x2 plus iy2. That will give me x1, x2 minus y1, y2, and then x1, y2 plus y2, y1, x2. This, if I write it like this, it's not entirely clear how we came up with the right hand side, but since I've already said that structure, so here I need structure on S1 arises by, so I already said that one can think of S1 as complex numbers with unit modulus, and then one can get this structure. So this is how, so this is the group operation, and we know that S1 is indeed a group. The identity element is literally the complex number 1, which would correspond to the point 1, 0 in R2. And we know that the inverse of an element with modulus 1 is also another element with modulus 1. So this is the operation, and in fact the inverse, I can even write down the inverse. So inverse of x comma y is just it's just the complex conjugate of this, so it's x minus y. Right. So, and so this, since we have explicit formulas for group multiplication and the inversion operations, it's immediately clear that, again, by using the fact that these operations are actually well-defined maps on all of R2. So when we restrict it to S1, we'll continue to get smooth maps. So therefore, the group compatibility condition, which I talked about here, this stuff is satisfied for S1 with this operation. So S1 becomes a Lie group. The group structure on S3 is, well, again, one can think of S3 as a subset of S3 is a subset of R4, which is C cross C. However, it's with C cross C with all those elements with norm equal to 1. However, the group structure on S3 is not immediately, it's not clear. In fact, the S1, the group operation on S1 is, since it's coming from C, complex multiplication, it's just an commutative abelian group. It doesn't matter whether I do x1, y1, whether I put this one first or x2, y2 first, I get the same answer. But the group operation S3 is actually, it's a non-abelian group operation, and it's not, immediately clear how one sees that this is a Lie group. But it's not that difficult either. But however, I will not go into that. Instead, I'll talk a bit about matrix groups, which are the most important classes of Lie groups. As it so first let's start with GLNR. Now here it's the operation is just matrix multiplication. Group operation is matrix multiplication, and if so, one has to check that GLNR cross GLNR to GLNR, A comma B going to A times B, whether this map is smooth or not. Well, we do know that first of all GLNR we have seen is just an open subset of MNR, the set of all n cross n matrices, which is Rn square. So when talking about smoothness, we can just use the fact that this is an open subset, and so the issues regarding smoothness are just we can think of this as maps of corresponding the Euclidean space Rn squared cross Rn squared to Rn squared, and matrix multiplication is just corresponds, will give rise to a polynomial map in these variables, input variables. So therefore this is smooth. And similarly inversion, GLNR to GLNR, the map is A going to A inverse. Here it is still smooth, but it's certainly not going to be a polynomial operation. The entries of A inverse are not polynomials in the entries of A, but they're the next best thing. They're rational functionals. So entries of A inverse are polynomials in the entries of A, not polynomials, sorry, rational functions ratio of two polynomials Well, rational functions can cause problems if the denominator is becomes 0, but here the denominator we know is denominator equal to just the determinant of A, and since A belongs to this open set GLNR, it's not going to be 0 anywhere on this set. So it's a rational entries of A inverse are rational functions with non-zero denominator. Therefore, it will also be, they'll be smooth. So both of these are smooth. So therefore, GLNR is a Lie group. Once we have this, we can immediately see that. Hence, we don't have to repeat the calculation here. Hence, ONR. The other two matrix groups we considered are these two are Lie groups as well. Well, why? Yeah. So I added this word hence. So this is supposed to follow from whatever this discussion about GLNR, and that's again to do with the fact that these are submanifolds of GLNR. Note that this operation, matrix multiplication, so let's call this one as phi1 and this is phi2. Matrix multiplication and inversion, phi1, when I do ONR times ONR, we know that the product of two orthogonal matrices is, after all, this is a subgroup, so matrix multiplication preserves. So the same phi1 that I had here, when I restrict it to ONR cross ONR, it will go back to ONR. And similar thing for SLNR as well. When I restrict this product operation, this is the very definition of a subgroup. So, and phi1. Similarly, phi2 will take ONR to ONR and SLNR to SLNR. So, since we have already established that phi1 and phi2 are smooth on the big manifold GLNR, we can use our earlier remarks about smoothness of maps when restricted to submanifolds to conclude that this phi1 and phi2, when regarded as maps from ONR cross ONR to ONR and ONR to ONR, similar for SLNR, they are also smooth. So we conclude that by our earlier remarks about smooth maps restricted to submanifolds both in the domain and image, we see that the restricted maps are smooth. Therefore, we get that these are Lie groups as well. Now, the reason for bringing up this notion of a Lie group in the context of vector fields, after all we were talking about vector fields, is not clear from what I have said so far. So in my next lecture, I'll talk briefly about that vector fields on Lie groups and see the role that they have to play. So, okay, so we'll end the lecture today at this stage. Thank you.